Okay, so in this video we are going to review some important features of inductors and then look at a few examples. So let's remember our equations here. First off, the equation is that the voltage across an inductor is equal to the inductance times the derivative of the current. And we also know that the energy stored in an inductor is equal to 1/2 the inductance times the current through the inductor squared. Now some other important things here. Remember, for a charged inductor, and I like to think of this in DC cases because that's typically what we're looking at. There is no voltage across it. So charged inductors behave as shorts. And then a finite amount of energy can be stored in an inductor. And again, that just comes from the formula just like we have with capacitors. And clearly the larger the inductor, the more energy that can be stored. It is impossible to have abrupt changes in the current for a charged inductor. And if you remember at the end of the previous lesson, that was referring to an inductor being used as a choke, to choke spikes of current out, and also in surge protection circuitry. If you just Google surge protection circuit, you'll see that there's inductors in them. And there's actually usually two inductors. There's an inductor on the hot line and an inductor on the neutral line, just so that, if you get spikes of current in either way, because you put it on the neutral line too, because that's like the path that closes back to the power company, and if somehow your device malfunctions and puts a spike out on the return path, you don't want that spike of current on the return path getting into the power grid. So those again are used in surge protection circuitry. And then inductors don't dissipate energy. Ideal, but they store them. And we know that, again, this is in an ideal case that inductors don't dissipate energy, but we know that has to be wrong just if we look at the way the inductors are built. Just going back to this little sheet here that we had, we can see that, it's a coil of wire. So while that coil of wire, with it being copper, might have a very low resistance in it, there is absolutely a resistance for inductors. In fact, sometimes the resistance is large enough to be able to measure with an ohm meter. There's some inductors that I have in the lab that are they're actually in the millihenry range, which is pretty large. and you can measure the resistance on them, and the resistance on those inductors is actually a couple hundred ohms, because there's just so much wire sitting there on them. So these actually absolutely will have resistance associated in them for real inductors. But for the ideal ones, which is what we're going to be looking at in this course here, they don't dissipate energy, they only store them. All right, so let's look at an example here. Let's look at, suppose we have uh, 2 millihenry inductor. The voltage saying the wrong thing. The current through the inductor is 5 sine of, we'll just say 2t. We're just making up some numbers here. Amps. So this is not DC. So we're not looking at the fact that this is ever going to behave as a short, because it's an AC signal, so it's constantly charging and discharging. The current through the inductor is 5 sine of 2t. And then we're going to have two things we're going to answer here. What is the voltage across the inductor? Actually, we're going to answer three things. What is the energy stored at t equals pi over 2 I'm going to do pi over 4 and pi over 2 seconds. And part C, what is the maximum energy stored in the inductor? Now, before we even look at this, when it says what is the maximum energy stored in the inductor, and the reason we're asking that is because remember what a sine wave looks like. It goes up and goes down. This is what a sine wave looks like. And so the current through the inductor is constantly changing. And it's now, you might say, hey, you can't change the current through an inductor. No, we can't change it rapidly. I can't have spikes of current. And what's happening here, this isn't a rapid change. You could say, well, it's starting at 0, and then you can just follow this up here. It's like, okay, well, then I get a little bit of current, 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 and I go all the way up to 5 amps of current, because it's 5 sine of 2t. And then, okay, some more time is moving along, and I'm slowly decreasing the current, so on and so on. I'm decreasing the current, decreasing it down to minus 5 amps. So I'm not doing instantaneous changes of current. So, you know, this doesn't apply in the sense where we're saying that, hey, you know, it is impossible to have abrupt changes. This is not an abrupt change. This is a sine wave that isn't an abrupt change. Abrupt change would look like this. If you had 5 amps and then you did this down to negative 5 amps. This here is an abrupt change. And that's what we can't do. We can't have an inductor do something like that. It can't go from 5 amps suddenly down to negative 5 amps. It takes time to do that. So when we say abrupt change, that's what we're referring to. All right, so let's go back and answer some of the questions here. So part A should be pretty straightforward for us because, again, we just used the formula that the voltage across an inductor is equal to L times the derivative of the current. Now again, just using our formulas for derivative of current, we get here the derivative of the current would be, well, it's going to be 5 times, then I bring that 2 out, and I get cosine of 2t. So this is simply just 10 cosine of 2t. And now we just plug in for my formula here that I've got, what was it, a 2 millihenry inductor. So 2 millihenries times 10 cosine 2t. And if we multiply that out, we would get 20 cosine of 2t millivolts. And this is how you can see we're not talking about an abrupt change here. Because remember, we said for an abrupt change we need infinite voltage. Well, here's what the voltage is. This is how the voltage is changing. Yeah, it's going up and down, but this isn't an infinite amount of voltage that we need. We need some millivolts of voltage. It's a very small amount of voltage we need to actually have this current changing with the equations that we have set here. All right, now part B, I'm just going to write it off to the side here, is saying what is the energy stored at t equals pi over 4 and pi over 2 seconds? Well, let's write our equation for energy down. We know that this is 1/2 L times the current squared. Now it's saying at 2 different times here. Well, that's because remember that our current isn't constant. Our current is 5 cosine of 2t. Now, you definitely, if you're not had any trig yet or anything, I'm sorry, it's not 5 cosine, it's 5 sine. If you haven't had any trig or anything, this is where you definitely want to turn to your calculator, but there's 2 things we need to make sure, or 1 thing we need to make sure. Make sure mode is radians, not degrees for your calculator. That's critical for us here. And if you're using just a scientific, often at the top of the calculator you'll see DEG for degrees, and then you'll have RAD for radians. And I'm going to see even if I can have it on this calculator here. Yeah, so you can see here degrees, radians, and there's even something called gradients. So right now it's in the mode degrees, but I would want to make sure to put it in radians. And this is just the calculator, Windows calculator, so it's nothing fancy going on here. It's just what I've done is instead of doing the standard, I've put it into the scientific mode here for it, because that gets me these sine functions and cosine functions, gets me the exponential function, things of that nature. Obviously, if you've got a calculator, you know, I've been using my graphing calculator. You can download calculators for free on your cell phone. I've got one on my cell phone that I use all the time. But the key thing is we need to make sure it's in radians to do this problem. All right, so the next step here then, of course, is we need to figure out the current at these 2 different times. Well, all we do is plug in t equals pi over 4 and pi over 2 to determine the 2 currents. So there's going to be 2 answers here. We're going to have what's the energy stored at pi over 4 seconds, and we're also going to have the energy stored at pi over 2 seconds. All right, well, if I do that, IL for one of them would be 5 sine of pi over 4 times 2, which would be 5 sine of pi over 2. Now, I picked these values on purpose because it turns out that these work very nicely. But just to show you on your calculator here, if I do pi divided by 2, see what that is? Okay, I get 1.175. And then I do the sine function of that, I get just 1. Now, I did that on purpose here. I picked those numbers on purpose. So this gets me 5 times 1. So the current at pi over 4 seconds is just 5 amps. Now, if I do this at pi over 2 seconds, this would just be 5 sine of pi. And then, again, if you've had trig, you might know what the answer to this is, but this is where we can use our calculator. Pi, and then we do the sine function of it, and we get 0. Now again, make sure that you're in the correct mode. And I'm just going to show you here why that is critical in just a second. 5 times 0, of course, is then 0 amps. So at pi over 2, we have 0 amps of current. So the reason it's important that you're in the right mode here is if I do, for instance, pi and the sine of that, which we know is 0, but if I do it and I'm not in the right mode, it doesn't give me 0. It gives me 0.0548 because it's assuming it's not looking at that as radians, it's looking at it as 3.14 degrees. So that's why you need to make sure you're in the correct mode for your computations. All right, but the next part of this here is pretty straightforward because we have the currents now, and we know that energy is just 1/2 inductance times current squared. So this is just going to be 2 millihenries times, in this case, it'd be 5 squared. So we have 2 millihenries times 25, which would be 50 millijoules. And then for the other one, we have still 1/2 L I sub L squared. And in this case, we would get 1/2, and I can't do computations here. I'll go back and fix that in a second. 1/2 2 millihenries times 0 squared, which is 0. And you probably all noticed this and are screaming at me right now. I forgot to keep that 1/2 here. So really this is 25 millijoules, not 50. And I always joke with some of my classes, I'm like, I've demonstrated, a common mistake here for you. And I was just seeing if you could, if you were paying attention to catch that mistake, which of course, I joke with people like that. We all make mistakes, but definitely be careful with that. I forgot to carry that 1/2 down to the next step, which of course affected my answer. But of course, in the case at t equals pi over 2 seconds, we have 0 joules of energy stored. Now, we shouldn't, again, be too surprised by this. The current, let's just go back here, the current is constantly changing. So at some instant of time, there's going to be no energy in that inductor. That makes sense. Now, part C, we want to know what is the maximum energy stored in the inductor. We actually, I say, already have the answer to this. And the answer here is 25 millijoules. And how do we know that? Well, let's go back to what these sine and cosine functions look like. So they go up and down, right? And we say, okay, well, whatever the number is in front, that's the maximum it gets to, and it's also the minimum it gets to. So we want to know what the maximum energy stored is. Well, the inductance doesn't change. The inductance is 2 millihenries. The only thing that's changing is the current. So we need to know, well, where is the maximum current? And just looking at this, we can clearly see that 5 amps is the maximum current. And I already did that computation. 5 amps being maximum current. I did 5 squared times 2 millihenries times 1/2 and got 25 millijoules. So part C, we actually already had the answer for. But even if we didn't have the answer for it, it's still easy to do because you just kind of sketch out the sine function. Or even if you have a cosine function, remember, cosine function looks the same, except instead of starting at 0, we start at the top. So this would be a cosine function. All right? And I wanted to do another example, but this video is already at 20 minutes, which is pretty long. So I'm going to stop this video, and we're going to do another example on inductors.